Hello everyone. Welcome to the day 8 of the machine learning teach by doing project. This is the part 2. In the part 1 we learnt about Jupyter notebooks. We learnt how to install Jupyter notebook and how to integrate it with VS Code. In part 1 we also learnt about three powerful Python libraries: NumPy, scikit-learn and matplotlib, and we installed them in our VS Code editor. So, if you have not gone through part one, please go through it because we will be needing all of these libraries which we have installed when we run the code in today's particular lecture. So, in this lecture, what we will be doing is that we'll actually be running the random linear classifier algorithm in Python, and we'll be seeing the results for ourselves. So, in the two lectures before the previous one, we looked at linear classifiers in theory, right? We looked at this particular random linear classifier algorithm. We also looked at the hypothesis class. We looked at this sine function which exists, this sine function. And essentially, we made all these notes about the theory. Towards the end, we looked at cross validation error and we saw the difference between training error, validation, and test error. Today, we'll be actually diving into code. So we will be employing all of our learnings into code. If you have not been through those two theory lectures, I highly recommend you to go through those so that you will appreciate today's lecture much more. So let's get started. In this lecture you will implement the random linear classifier algorithm in Python. And I also show you the best tricks to get started with Python if you are a beginner. Even if you are a complete beginner in Python, I have designed this video so that you will be able to follow and understand. So let's get started. So in this is the day 8 of the ML teach by doing. Right. And our aim in this lecture is to code the random linear classifier algorithm in Python. Let's see the tools which we will need for this coding. The tools which we will need is we will need Python to be installed. We will need VS Code to be installed. We will need Jupyter Notebook to be installed. And we will also need scikit-learn. Not just this, we will need scikit-learn. We will need NumPy and matplotlib, which is the plotting library, to be installed. So scikit-learn is the library for ML in Python. NumPy is the library for scientific computing, and matplotlib is the plotting library. We'll need all of these three installed. And we have done this in the previous lectures. These two have been covered in lecture 5 of this teach by doing course. So please go to this lecture to see how to install those. All of these have been installed in the previous lecture, the part 1 of the practical implementation of the random linear classifier algorithm. So in the preceding lecture we have installed Jupyter notebook, we have installed scikit-learn, NumPy and matplotlib, and we have even configured them with VS Code. So all of the tools are in place. The next thing which we need is the problem itself. So if someone is seeing this lecture for the first time, and if you have not been through the linear classifiers previous lectures, so here is the problem again as a refresher. Essentially, the problem of this linear classifier looks like this. On the x-axis, we have whisker length, which is x1, and on the y-axis, we have the ear flappiness index, which is x2. And then this is the data which we have for dogs, which is the first class. This is the data. And for cats, this is the data. Cats generally have higher whisker length and lower ear flappiness index than dogs. That's why the data looks like this. And the aim is to find the that straight line or that linear classifier which best separates the two sets of data. And mathematically, this is also given as theta 0 plus theta 1 x1 plus theta 2 x2 equal to 0. To understand the code which we are about to write, we will first need to understand the random linear classifier algorithm itself. So we have already covered this in the previous lectures, but let me introduce it here for reference so that it's there in front of your eyes when we code. In case you have forgotten it, the only way to understand the code is to first understand the algorithm. So the algorithm is called as a random linear classifier. Random linear classifier. And the aim of this algorithm is to find the best or find the optimal values of theta 0, theta 1 or and theta 2. So basically find the optimal straight line here. Because if theta 0, theta 1 and theta 2 are fixed, this straight line is fixed. So we essentially saw that there are three steps to execute this algorithm. Step number 1 is try k random choices. Step number 1 is try k random choices of theta 0, theta 1 and theta 2, and we actually chose this k to be 100. Step number 2 is compute the training error for each of the k hypotheses. For each of the k hypotheses, and the final step, which is step 3, is choose the hypothesis with the lowest error. So these are the three steps of the random linear classifier algorithm. Visually, this algorithm is really very simple. What it tells us to do is that take, let's say, 100 different, where k is equal to 100. Try 100 different straight lines. The first straight line might be this. The second straight line might be this. The third straight line might be this. The fourth straight line might be this. Try 100 different straight lines and choose the straight line which gives you the lowest possible training error. That is the algorithm. It's as simple as that. Now, the way the training error is obtained is that uh, so this is how the training error is obtained. Let's say the hypothesis which is chosen is some theta star or theta 1 star x1 plus theta 2 star x2 plus theta naught star. Remember that this is not the ultimate or the final algorithm. This is probably the algorithm, or this is the hypothesis which is chosen in one of the 100 iterations which we are going to try. The way the training error is computed is that you remember we had this sine function before, the mathematical function sine, this one, sine function, which basically determines if the point is on the positive side of the normal or the other side of the normal to the straight line. So the sine function is defined as like this. So basically, if something is on the plus side of the normal, then it is uh, positive or classified as plus 1. If it's on the other side of the normal, then it's classified as minus 1. So basically, how the training error is evaluated is that for all points, you compute this. For all points, you compute this. For all the training points, basically, for all the points, you compute this. And these are the training points. If the answer is greater than 0, if this value as given by our hypothesis is greater than 0, then your hypothesis will predict the answer to be plus 1. Whereas if this value is less than 0, then our hypothesis will predict the value to be minus 1. And based on these predictions, that's how the error is computed. So let's say the hypothesis predictions for different points are, let's say the hypothesis prediction for this point is minus 1, for this point it's plus 1, for this point it's minus 1, plus 1, etc. Similarly for all points. And we know the ground truth data, right? The ground truth data is that all the dog points are plus 1, all the dog points are plus 1, and all the cat points are minus 1. This is the ground truth data. The way the training error is computed is that for the hypothesis which we choose, this value is computed for all the data points, the value which is predicted by our hypothesis, and then it is compared with the actual value. And based on this, the number of errors are computed. If this was a bit too fast for you, you can go to the second lecture on linear classifiers, where we actually took two hypothesis functions, h1 and h2, and we computed this training error using a hands-on example. So now I'm not going into that detail because we have already covered that in the previous class. But now I just want you to remember the intuitive feel for what we are or how we are calculating the training error. That's it. This is the simple algorithm. Just remember the three steps. We are going to try out k random choices or 100 random choices of the hypothesis. We'll find the training error in each choice, and then we will choose the hypothesis with the lowest possible error. That's it. Now let's go to the code. Let's jump into the code. We already created this sample.ipynb file in the previous lecture. For the first code which we'll be looking at today, we'll be looking at a file which is named as classification.ipynb. I'll be sharing this file in the material which I share, so do not worry. And I'll be explaining every single code block which I have written and also explain the results. So let's start with the Python script. If you are new to Python, this may be your first Python script. But the way I always approach any new coding language is directly get your hands dirty. Directly start with some code like this. And as you execute the code, you try to learn about what is written in the code. So I already explained in the previous lecture how to load different cell blocks or coding cells in a Jupyter notebook environment. So this is the first cell, and there are two commands here: import numpy as np and import matplotlib.pyplot as plt. So let me run these two commands. Now it's run. as is shown by this tick symbol here. What this command actually means is that uh, we are importing the libraries numpy, which is used for scientific computing, and we are also importing the library matplotlib, which is used for plotting. So these are the two libraries which we are importing in this particular code. Since we will need to do some scientific computing operations, some array manipulations, as I will show you, and we'll also need to plot some material. That's why we have loaded these two libraries specifically, NumPy for scientific computing and Matplotlib. And the way to write the code for this is in Python is import NumPy as NP and import matplotlib.pyplot as PLT. So in the rest of the code, the way to access these libraries is just by using these variables np and plt. So I've run this code block now. The tick sign is shown. The next thing is I determine or define a random seed. The thing is in machine learning algorithms or in machine learning codes, every time you run the code, some different initial condition might happen, and that might lead to different results. For you to have the same result every time you run your code, this particular command is very important. Now if you run this command and if you want to know further about it, what you can do also is you can highlight this and you can click on the right and click on go to definition. So here it says that random.seed. Still, if it's not clear, what you can do is you can copy paste this, go to Google and just paste it. And the documentation for NumPy is so extensive that whatever doubt you have, it will immediately be clarified. So here I have asked what does np.random.seed do, and here you can clearly see that it makes the random numbers predictable, which means that every time you run that particular thing, the same random numbers are generated. Essentially, this thing is used to make sure that your code is initialized the same way every single time. This is how you learn about coding. You first execute that particular command, see the result, and then search about what you don't understand. So these are the first two code cells which we have run right now. The third code cell is loading the data itself. So as I showed you here, let me go to the drawing board. As I showed you here, there are two variables, ear flappiness index and whisker length. And this is the dog data and the cat data. So first we are going to generate the dog data. The dog whisker length, which is the x coordinate, is given by this particular function. And the ear flappiness index is given by this particular function. Let me tell you what this right hand side actually does. np.random.normal basically is a normal distribution or a Gaussian distribution. So for those of you who do not know, a Gaussian distribution looks something like this. So this is how a Gaussian distribution actually looks like. So when I actually wanted to generate the dog data, especially the data for the whisker length for the dog, I wanted to generate a lot of data around 5, whisker length equal to 5. So I told Python to generate the data from a distribution like this, which has a mean equal to 5 and which has a standard deviation of 1 and size of 10th, which means that the number of data points which we have in our data is 10. Similarly, for the ear flappiness index, I told Python that I want data from a normal distribution whose mean is equal to 8, standard deviation is equal to 1, and the number of data points is equal to 10. So this is just the choice which I have made for generating data. You can even write random or you can even choose random data to start with. So let me actually run this. So now the data is generated. If you want to check the data, let me see. So let me type dogs whisker length and let me run it. So you can see this is the data which has been generated. As you can see that the mean for this data will be 5 since I've generated it from a Gaussian, and the standard distribution and the standard deviation is 1. So generally you can see that all the data is generally between 4 and 6. Essentially you can think that this median value, this thing is equal to 5. This thing is equal to 5 for the data uh, uh, which we have sampled. This is equal to 4. This is just a crude visualization. It's being difficult to type here, but so but this basically this is equal to 4 and this is equal to 6. So we are basically sampling data in this range. This is where the x coordinate is being generated from. This is where the x coordinate is generated from, dog whisker length. And now let us actually see the y coordinate, dog ear flappiness index. So this is how the ear flappiness index looks like. See here the mean is equal to 8 and the standard deviation is equal to 1. So generally all the data will generally be between 7 and 9 with the mean of 8. So this is the dog data which has been generated. Similarly, here is the cat data. Now for cats the whisker length will be higher, right? So the mean is 8 which I have given here, which is higher than for the dogs where the mean was 5. And for the cats the ear flappiness index will generally be lower than dogs. So for dogs the mean was 8 and for cats I have chosen the mean to be equal to 5. So then the cat data has been generated. Instead of even showing you how the cat data looks like, let me just plot both these data sets. So first thing I want to show you is the use of NP here. See here we are doing a operation, right? We are generating a normal distribution, and that is being done using the dot random dot normal command in the NumPy package. And the way we specify that this is a function in the NumPy package is using NP. So here you see at the start, we have import NumPy as NP, import NumPy as NP, and this is where this NP is used. Now, when I want to plot, I will use PLT. So here you see import matplotlib.pyplot as PLT in the second line. So every time I want to plot, I will use the command PLT. So plt.scatter, plt.scatter, etc. So here what I'm doing is I'm plotting scatter plots. In the first line, I'm plotting a scatter plot of the dog whisker length and dog ear flappiness index. So here you can see that it's shown with the blue. So this is where the dog data actually it looks like, and the orange is where how the cat data looks like. So what I did is I first plotted the dog data, I then plotted the cat data. Then I told this plot what the X label should be. I told this plot what the Y label should be, and I told this plot what the title should be. And towards the end, I wrote plt.legend, which means I want to show a legend. And how and what is shown in the legend is determined by this thing. So if I want to say dogs data here and cats data, you will see that the legend will change over here. See, it changed from dogs and cats to dogs data and cats data. Let me again bring it back to dogs and cats. So now it's being brought to dogs and cats. So this is how the plotting in Python works. Now the way I think about learning a coding language is if you want to understand about plotting, instead of going through this matplotlib library and learning about everything, the next time you plot, you can just take this code as reference and you can tweak the parameters in this code to generate a new plot of your own. And that is how you learn. There are several other things which we can do with this plot. We can add the X ticks here, we can add the Y ticks, we can add a scale bar, we can change the background color. So many things which can be done using the matplotlib library in Python. So this is how the data set actually looks like. You can see that I have constructed this data set to be quite similar to the data which we had in the whiteboard demonstration. Uh, Great. So the first step is done. The data has been constructed. The second step is implementing the random linear classification algorithm. Now remember the intuition behind the algorithm, and then the code automatically becomes very easy. There are just three steps. We are going to try out 100 choices of the straight lines. We are going to compute the training error for each of the choice, and then we are going to choose the hypothesis with the lowest error. That's it. Let's see how this is done in the Python code. We define a function in Python using something like this: def, then we write the function name, and then we specify the input which this function would take. This function will essentially take four input parameters: data of the dogs, data of the cats, k, which is the number of choices we are about to make. So here we saw k was equal to 100. And then the last input is d. D is basically the size of the theta 1 and theta 2. So in our case, D is equal to 2, which is essentially the number of features. So we just have two features here, right? The whisker length and the ear flappiness index. So D is equal to 2. I'll tell you where D is actually used. It's used, uh, so we want theta 0 plus theta 1 plus theta 2, right? This is where D is actually used. Because there are two parameters here. So if you see theta is composed of theta 1 and theta 2, and theta naught is the third parameter. So essentially what's written in this code is that uh, this thing was theta 0 plus theta 1 x1 plus theta 2 x2, right? In a matrix form, this can also be written as theta transpose x, where theta is a vector with two dimensions, theta 1, theta 2, and x is also a vector with two dimensions, x1 and x2. So since here there are two dimensions or two variables, d is equal to 2. But remember that all we are doing is just this: theta 0 plus theta 1 x1 plus theta 2 x2. That's it. Okay, so these are the inputs: the cat data, the dog data, the k value, and the dimensions of the, or you can even think of d as the number of features. So I'm just going to write here d is the number of features. So we have two features, right? Whisker length and ear flappiness index. That's why d equal to 2. Now let's see how this particular algorithm functions. Here we define, so for range of k, which means we are going to repeat this 100 different times. In each iteration, you choose some theta and you choose some theta naught randomly. So here again this np.random.normal is used, which means you randomly select theta and theta naught. And then you find the error between your prediction and the actual data from this compute error function. Let us look at the compute error function. The compute error, what it does is it calculates np dot dot, which is like a dot product between theta and the dog data, and it computes the np dot dot, which is the dot product between theta and the cat data, and then it adds it with theta naught. Basically what it does is exactly this thing. So this can also be written as the dot product between theta dot x plus theta naught. So what it's showing is that you calculate it for the dog data, you calculate it, and for the dog data the actual value should be equal to plus 1, right? What we have already seen here. So what is written in the code is that you calculate this value for the dog data, and if this is equal to minus 1, then there is an error. So basically you calculate the value of theta dot x plus theta naught. Let me write theta transpose x plus theta naught. For dog data, if it is minus 1, then there is an error. So remember, this is the hypothesis prediction. This is the hypothesis prediction. And then for cat data, if it is plus 1, then it is an error, because the actual value for cat data is minus 1, as we have seen over here. So for the dog data, if the hypothesis value is minus 1, then there is an error. For the cat data, if the hypothesis value is plus 1, then there is an error. And what is the hypothesis value? The hypothesis is just theta 1 x1 plus theta 2 x2 plus theta naught, which is also written as a dot product. So this can also be written as a dot product. So np dot dot between theta and x. This is a dot product in linear algebra. That's all the math which you need to know uh, until this point. So what this code is actually doing is very similar to what we discussed. For dogs, if that dot product is less than 0, then error, then there is an error. For cats, for cat data, if that dot product is greater than 0, then there is an error. So very simple basically. So essentially, in the random classifier algorithm, what it's showing is that you do the calculation for k times, which is repeated for 100 times, and in each repetition, what you do is you choose a random value of theta and theta naught. You choose a random hypothesis, you compute the error as is defined in this function, and you choose the hypothesis with the best error. So let's say in the first iteration, the error is 5. In the second iteration, if the error is 2, then you replace the best error with the current error. Now, in the another iteration, if the error is 0.5, then the best error will be that error, and the best theta and theta naught would be that particular iteration which gives the lowest error. So simply what we are doing is exactly what we started with discussing. You choose 100 different 100 different linear classifiers. For each linear classifier which you choose, you compute the error, and you ultimately choose the linear classifier as your best hypothesis which has the lowest possible error. That's it. That's all this code is doing. And if you look at the compute error function and if you try to understand it, it's very similar to what I explained here. Essentially, what it says is that, let's say if you have a dog point and if you have a hypothesis, you calculate theta 1 x1 plus theta 2 x2 plus theta naught for this point. That's the hypothesis prediction. If that prediction is minus 1, there is an error. Similarly, for the cat point, if that prediction is plus 1, there is an error. That's how you evaluate how good your hypothesis is. Now you are also introduced to this dot function, right? Which is basically the function in linear algebra. Whenever you write Python code, this theta 1 x1 plus theta 2 x2 plus theta naught is also sometimes written in terms of linear algebra, like a dot product between theta and x, and then you add it with theta naught. That's just the mathematical representation so that the code becomes easy. But many students think that ML is extremely complex maths and I don't know about this dot product and all, so they just leave it. But underlying, you just write down the equation and it turns out to be a simple equation like this. So this is the algorithm which we have written. This is the classifier function which we have written, the random linear classifier. Now is the time to actually execute the algorithm. To first execute the algorithm, we first prepare the dog's data and the cat's data in a proper format. So let me show you how the dog's data now looks like. This is just a pre-processing operation. So here the dog's data looks like this with x and y coordinate written like this. Earlier we had only defined the x coordinate separately, right? Dog whisker length and dog ear flappiness index. But now we need to define one single point as an x and a y coordinate. And that's what this vstack function does. It stacks the whisker length and the ear flappiness index together so that the dog's data starts looking like this and the cat's data starts looking like this. Here you see this is how the cat's data now looks like. And now we are ready to actually run the random linear classifier algorithm or the function. So remember that this function takes in 4 arguments: dog's data, cat's data, k, and d. Dog's data and cat's data we have already pre-processed in the correct format. We are choosing k to be equal to 100 and d is equal to 2, which is the number of features. So let's run this. And let's just print the best theta. This is the best theta. So this is essentially theta 1 and theta 2 in our whiteboard. And now let us plot the base theta naught, or let's print the base theta naught. So this is the base theta naught. So the answer which our algorithm has given us is, let me go through it again. Theta 1 is minus 0.68, theta 2 is 0.66. So this is minus 0.68, this is 0.66, and theta naught, which is the best theta naught, is minus 0.46. This is minus 0.46. That's the output of our algorithm. Now you see, whatever we looked at in theory, it's actually quite easy to implement it in Python, and we even recovered the best possible answer. But this is not enough. I want to show you how it actually looks like if we plot it against the data. So here we have again, so the answer which is the best answer, it's also called as the decision boundary. And the decision boundary is basically the best straight line which classifies the dog data and the cat data. So here you can see that this is the answer which we got, and it separates the dogs and the class cats beautifully. That's amazing, right? So essentially, we started out with the problem of finding the best linear classifier using the random linear classification algorithm. And this is the red line is the answer which the algorithm gave us. You remember in the previous lecture, we also looked about, we also saw the training error and the testing error, right? And we saw that how machine learning practitioners actually divide the data into two parts, into training data and testing data. So let us look at this in further detail, because up till now, in this particular code, we just had training data, right? We did not even divide the data points. So let's say if we look at this data points, all of it was used as the training data. But what about test data? How do I know that this red line, which is my correct answer, will actually classify the test data well or not? How do I know that it performs well on a real test, like in an exam? So we will exactly implement what we had discussed in this lecture. We had discussed that what machine learning practitioners do is that they leave out some data for testing. So this is the test data, and they retain most of the data for training, but they leave out some data for testing. And then they test the best algorithm which they have found on that test data to see how it is performing. So the algorithm, which is the random linear classifier algorithm, is run on the training data itself, but we have left out some test data on purpose to check how the algorithm is doing on the test data. So let us now implement that in practice. Most of the code remains entirely the same. So now I have constructed a new notebook which is titled as classification underscore train underscore test dot ipynb. Most of the notebook is exactly the same as this normal classification notebook. The only difference is that we will use a we'll essentially use a function called train test split, which automatically splits the data into training and testing. This is where the library scikit-learn becomes very important. So you remember we installed scikit-learn, right? And I told you it's a machine learning library. So if you manually want to classify the data into training and testing, you can do it. But the scikit-learn already automatically provides you the function called train test split. You just import the data and it splits it into training and testing. So let me run this. As you see, this part is the same where we have a random seed generator. The data is also the same. The total data has 10 points with dog whisker length, dog ear flappiness index, cat whisker length, and cat ear flappiness index. Everything else is generally the same. The only difference is we now divide the data into training and testing. So what we do is that this train test split function, which is given by scikit-learn, it needs some inputs. It needs the data and it needs the labels as inputs. So basically, let us see what labels actually are. So if you see the labels, Great. So basically, dog data is is zero label and the cat data is one label. So this X train, X test, Y train, Y test just needs to know that which is the first class and which is the second class. So all the dog data is labeled as zero, all the cat data is labeled as one. Uh, some other argument which it takes is that test size, which means that how many data points which we want as training or how many data points which we want as testing. So if test size is zero point 0.2, it means that 20% of the entire data is reserved for testing and 80% will be used for training. So let me run this particular code and let me plot the X test. So we had 10 dog data points and we had 10 cat data points, right? So overall we had 20 points. And here you can see when you run X test, 4 points out of those have been used for uh, 4 points out of those 20 have been used for testing, which is zero point 0.2, which is 20% of the data set has been used for testing. And if you do X train, there will be 18 points here. Sorry, there will be 16 points here, which means those are used as the training data. So that is the difference between this code and this code. In this code we are not using all the 20 points as training. We are using only 16 as training and the remaining 4 as test. There is also one more argument here called random state. This is again to make sure that the initialization happens in a similar manner, and then every time you run the code again, some new things do not happen due to randomization. So that's why random state is used. So everything else again is the same. Let me we just have defined these labels here so that the this train test split understands the two types of data which are present. Now let us visualize actually which data is used in training and which data is used in testing. So if you look at this cats and dogs data, here everything was used for training. But here if you see these two dark blue points here, they are used for training data for dogs, and these two reddish points here, they are used for training data for cats. I apologize for viewers who have a bit of a difficulty in distinguishing between colors which are similar. I'll try to be a bit better in the next videos in terms of the colors which I use. So here dark blue are the true two testing points which are used for dogs, and dark red are the two testing points which are used for cats. So overall there are 4 testing points and the remaining are the training points which are 16. Now everything else remains the same. Here you see the random linear classifier algorithm is exactly the same. The compute error function is exactly the same. The only difference is that now the random linear classifier is run on the training data, which has uh, only 16 points instead of having all the 20 points. That's it. So here you see how we have given the input. So random, this is the dog data because the Y train, the labels which we gave to the dog data are 0. This is the cat data because the labels which you gave to the cat data are 1. Again, the K will be equal to 100, which is the number of iterations, and D will be equal to 2, which is the number of features. So let me run this and let me do the final plotting again once more. So here you can see that this is the final plot. This is my training data line. This is the training decision boundary, and I can see that it classifies the training points pretty well. But unlike this code, we are not going to stop here. We are going to calculate the performance of this best fit line with the test data. So here we see we computed the training error which is 0, but we go a step further here and we compute the error on these 4 points which were left out. This point, this point, this point on, and this point. We are going to calculate the test error on the 4 points which are left out. So here you can see that the testing error is also 0, which is perfect. This is exactly what we needed. And let us plot this actually to see how the actual data compares with the predicted test data. So if you see the two red circles here, that is the actual dog data. If you see the two orange circles here, that is the actual cat data. Now if you see the crosses, the crosses are the predicted dog data, and the crosses is the predicted cat data, which means that our prediction is perfect. The prediction which we had, so essentially the prediction which we have for dogs is that it's plus 1, and the prediction which we have for cats is that it's -1, and it matches with the actual data. So this is just a visual representation to show that the prediction matches the data. This is not the actual prediction value, because the prediction value is just +1 or -1. So this thing is the most important, the testing error. So the testing error is also equal to 0, which is brilliant. So if I were a machine learning engineer, I would rate this second code much higher than the first code, because the first code does not split it into training and testing. So how do I know that if my algorithm, or if the best line which I found sees any new data, it's going to classify it correctly? How do I know? There is no way to know that, since I utilize all of the data for training. But in the testing data, I am sure that my algorithm is a bit more generalizable, because even if I leave out 4 points, I can see that it does pretty well on the 4 points which it has not seen. This makes me believe that if there is a new data point which it has not seen, my algorithm will generally do a good job on it. So here we saw the training and the testing. Now we are going to see one more thing which we looked at in the last part of the previous lecture, and that is cross validation. So let me again explain cross validation here. In cross validation, what is done is that up till now, up till now we saw this, that if you have a data set, if you have a data set, in case one, you use all of it as training data. In case two, you partition it. So then this is used as training, which is around 80% as what we saw in the current example. And this is used as testing, which is about 20%, as what we saw in the current example. Now the problem is that training and testing helps us to evaluate the hypothesis, and it helps us to evaluate whether the hypothesis does a good job on the testing data, but it still does not tell us how the learning algorithm itself is doing. In the previous lecture, or in the second part of the linear classifier lecture, I make a very important distinction. The distinction about what is the difference between uh, measuring the performance of the classifier and measuring the performance of the learning algorithm. So up till now, we have measured the performance of the classifier. So splitting the data into train and test is very good for measuring how the classifier does, right? Because here we measured how this particular classifier does on the test data which it has not seen, and we saw it does quite well. But what about the learning procedure itself? What about this algorithm itself? Or in today's lecture notes, what about this algorithm? How do we evaluate whether this algorithm itself is correct or not? How do we evaluate this? To evaluate this, in the second part of the linear classifiers lecture, we saw that a technique called as cross validation is used, and we are going to implement that. The objective is that, why did we randomly use 100 choices here? See, here we have randomly used k equal to 100, right? We randomly use k equal to 100. So let me change k equal to 200, uh, and see what this decision boundary is. Here I can see that this decision boundary hits this particular point. So it's not that good. Now let me change k equal to 200, and let's see what the decision boundary is. Okay, this is great, right? Because now the decision boundary is much better. It separates both the classes pretty well. It's not hitting one particular class, which actually shows that the value of 100 which we had randomly chosen earlier, the value of 100 which we have chosen is probably not the best one, which means that our learning algorithm was probably not the most optimal. Now let us try to find out the most optimal learning algorithm, or rather try to find the most optimal K using cross validation. In cross validation, what is done is that the split of training and testing is maintained, but the training data itself is further divided into these validation sets. So it's divided into these five sets called, it can be divided into more. I am performing a five-fold cross validation here. That's why I'm dividing it into five sets. And what is done is that in the first iteration, D1 is left out as test data or as validation data, and the algorithm is trained on this other D2, D3, D4, D5, and a hypothesis is found. That hypothesis is evaluated on D1, and one error is obtained epsilon 1. In the second iteration, D2 is left out, and then a hypothesis is found by training on D1, D3, D4, and D5. That hypothesis is evaluated on D2 to find the error epsilon 2. Similarly, we find epsilon 3, epsilon 4, and epsilon 5. Then we define an error called as cross validation error is equal to 1 by 5 epsilon 1 plus epsilon 2 plus epsilon 3 plus epsilon 4 plus epsilon 5. Now, this cross validation error is calculated for a huge number of values of k, calculated for a lot of k values. And then we choose that k which gives the lowest cross validation error. So this is how we evaluate the learning algorithm. What cross validation helps us to do is, without tapping the testing data, which is already limited because of the data being limited, the training data subsets can itself be used for testing. Parts of the training data are left out for testing. And that is how we check what's the best K which can be used. Once the best K is chosen, then the learning algorithm is defined or refined. And then the same procedure is repeated like we did for training and testing. So let us see how this cross validation looks like in the code itself. So I am again going to the train test code, and the data generation process remains exactly the same. The train test split, okay, let me go to this code. The data generation process remains exactly the same. The train test split also remains exactly the same. This plot also remains the same, where we see that 4 points are used for testing purposes. The algorithm also remains the same. The change is that this cross k-fold cross validation function which is defined now. Let me explain what this function does. So this is a k-fold cross validation, and this k-fold is a function which is defined in scikit-learn itself. So here you see I have imported k-fold here. Scikit-learn automatically gives so many functions like these which make our job very easy. So I don't have to write the entire cross validation procedure which I explained to you over here in detail. Instead, I just say that use a k-fold cross validation and n splits equal to 5, which means divided into 5 parts. That's it. So this is how I define that I want a 5-fold cross validation. And then what I told you is exactly what happens in this function. Essentially, one part is left out and that error is computed for each of the remaining part. And then we take an average of all the possible errors. And then the best k is that k for which the error is minimum. So first we define an array of k values, 1, 10, 50, 100, 200. We don't know which one is the best. And then this error, this average error which I also described here, this average error is calculated for all these k values, and then we choose that k which gives the lowest error, lowest average error. This is exactly what is written here. So the best k is the one which gives the lowest average error. So arg min means taking the lowest of all the errors. So what is done is that the average errors vector, it contains the average error for all the k values. and then we return the best k with the which has the lowest possible error. So let me run this function now and let me see what the best k is. Also, maybe let me try to have 350 also, just to see. So I run this right now, and I can see that the best value of k is 200. See, we did not expect this before, right? We randomly chose 100, but it turns out that for k equal to 200, the value of the loss or the error is the lowest. So we will use the value of k equal to 200. Then everything else remains the same. So instead of choosing k equal to 100 when we run our algorithm, we will choose k equal to best k, which means choosing k equal to 200. And then we do the same thing again. We plot the plot. It looks much better. Earlier you saw it was much closer to this initial boundary line. Now the separation looks much better. We calculate the training error, it is 0. We calculate the testing error, it is again equal to 0. And then in the last plot we again see the error, so there is no error. The actual data matches exactly with the data which we predicted. So this is the advantage of performing the cross validation procedure. We even optimize the learning algorithm this way. So when you integrate cross validation, two things are happening. You're optimizing learning algorithm, like which we did here, and then you're also optimizing the hypothesis by having the test data and by calculating the testing error. This is the difference between optimizing the learning algorithm and optimizing the hypothesis. So using this, finally, this is the answer which we have obtained. This dotted red line is the answer which we are looking for. But you see, machine learning is so beautiful and so detailed that if you give this data to someone, maybe they'll just draw this line and say that it's over. This is the best line. But there are so many details. There is training data, there is testing data, there is validation data, there is the choice of parameters, the difference between parameters and hyperparameters, and all of these needs to go into consideration when you write your machine learning algorithm and when you execute it in the first place. So I'll be sharing these code files with you for the simple classification with just the training data, and then also for the classification which has the training data, the testing data, and the validation data. And you can run these codes on your own. That's the best way to learn. So please don't be intimidated by these Python codes. I tried to explain every single thing to you in detail, right? Once you understand the theory, understanding these functions become very easy. Otherwise, without going through the theory, which we went through right now, and if you just, like, let's say we looked at this theta transpose x plus theta naught, right? If you did not see the theory and if you saw this np dot dot, you'll be confused and you will probably stop here. But it's actually very easy once you understand, or if you write down the mathematical equations which we did over here. Secondly, the functions in Python which we saw, such as the cross validation function, I did not go through this function in too much detail because it will take a bit of time. I'll probably allocate a separate lecture for it. But meanwhile, you can also go through this function in detail. The best way is to run it on your machine and then try to execute each line sequentially and see the output of that line. For example, if you don't know what np.vstack is doing, first run this code and see that you got the best value of k. Great. Now go back and try to understand what do these individual things mean. So np.vstack, you search about it and then you see that what this function does is that it stacks arrays in sequence vertically. That's it. And then you, with this understanding, you move to the next piece of line. And then you see that np dot zeros, what does it mean? This len, what does it mean? Try to understand this. Then errors dot append, what does the append function do? You will see that it appends the values to the vector which has been defined. Then np dot argmin, what does this do? Then try to search about it like this. And then you will see that it returns the indices of the minimum values along an axis. So see, it returns the index, it does not return the actual value. All of these things are very important to note. And the more times you will forget some of it maybe, but the more times you go through this documentation and the more times you try to understand the function, the better the grasp you will have on Python. This is how I learned Python. I ran these codes. I felt very motivated to see straight lines like these, which were my first ML algorithm in practice. That was awesome for me to see. That gave me motivation to further dive into these functions. So yeah, running codes actually initially that gave me a motivation to learn the details of Python, such as what is meant by this argmin function or vstack or hstack. And I feel that's the best way to learn any coding language. So there are two ways, right? The first way is you, let's say, learn the coding language, then you run the coding language, and then you and then you understand the theory. That's what many students do. But this leads to a lot of lack of motivation, because without running the code, if you just try to look at the code documentation, it's sometimes very demotivating. On the other hand, what I do is I first understand the theory, then I run the code, and then I understand the code. So that is completely opposite than the first process which I mentioned. Understanding the theory also makes it quite easy to understand the code, as I just demonstrated. So the whole pipeline should be understand the theory, run the code, and then understand the code. So beginners in Python, please run these codes by yourself, get the results, get these straight lines, which are your first ML algorithms, and then try to figure out what each individual functions means in Python. That's the fastest way to learn. So we actually had four lectures on linear classifiers. In the first lecture, we looked at the first three steps of any ML algorithm: gathering the data, generating the hypothesis class, and defining the loss function. Here we also looked at the sign function mathematically, and we compared two hypotheses and how to define the loss and the error function. In the second lecture of the linear classifiers, which is day 7, we looked at finding the algorithm, running the algorithm, and validating the result, step 4, 5, and 6. So we also saw the theory for this. We wrote the algorithm. We understood the difference between parameters and hyperparameters. We also understood the difference between testing error, cross validation error, and what is the difference between evaluating classifier performance and evaluating performance of learning algorithms. Only after making sure our foundational base was strong, we move towards coding. And in the coding lecture, we split it into two parts. In the first lecture, we looked at Jupyter notebooks, their introduction, advantages, and how to integrate with VS Code. We also looked at three powerful Python libraries: NumPy, scikit-learn, and matplotlib. And in the second lecture of this coding session, which is this video, we looked at how to code this algorithm in Python. We first looked at a file which just has training data, and then we looked at a file which has testing data and which then employed cross validation as well. I also showed you towards the end the best way to learn Python is to understand the theory, run the code, and then understand the code. The more time you do this procedure, you will automatically start getting a firmer grasp of Python, and at the same time you will have run many codes also simultaneously. Thank you everyone for following with me on this journey. We'll have several more things to cover later, such as is mentioned in this Microsoft course, we'll cover regression, we'll build our own web app, we'll cover clustering, natural language processing, and also we'll cover the fundamental aspects of ML as is given in the MIT's course: perceptrons, features, margin maximization, neural network, etc. So in this video lectures, you get the best of both worlds, theory as well as practice. And as you see from my lectures, I'm going through a lot of details of every single thing. I don't just make a statement and tell you to figure it out. I write it down in front of you and then I code it so that all of your concepts are completely cleared. So please follow with me through this journey, make notes, and run these codes which I'm going to upload in the video information. If you have any doubts, please ask it on the chat. This has been a bit of a longer lecture, but I deliberately made it long because I wanted to explain you guys everything. So please mention doubts on chats, run codes. If you are stuck at something, ask it in the comments and we'll reply as soon as possible. Thank you so much, and I'll see you in the next lecture.